Hi guys, so we are starting off here. I know we did this in the last video, but I still want to go back over it just so that way we can have a little refresher about what bond enthalpy is. In terms of what we're going to talk about in this video, I want to finish chapter 8, which is dealing with bond enthalpies. We're going to start chapter 9 and talk about the electron domain geometry, as well as getting into that molecular geometry or shape of a molecule. So let's go ahead and start with our bond enthalpy. Now, bond enthalpy is just a way that we can talk about the strength of a bond, and we can do that by determining how much energy is required to break a bond. Remember that a bond is going to have to absorb energy to be broken. Just like when we're forming bonds, we're releasing energy, which I know is kind of like backwards to maybe what we're thinking about, or maybe like backwards into maybe logic, I think. And that's a big common misconception. Remember that we said that when we break bonds, that means we're releasing energy. But really, to break something, we are going to have to apply some amount of energy before something's going to break. So we are requiring energy to break a bond. We can call this bond enthalpy. Now, we have, just like when we were talking about the enthalpy of formations, enthalpy of reactions from that thermochemistry chapter from chapter 5, we talked about, or we did some formulas where they were also, these values were found in a table where we had experimentally calculated all of these enthalpy of reactions before. We're going to have something similar here. We have found how much energy is required to break certain bonds on average in specific compounds, so we can just use those again. In this case, we have a chlorine bond, a chlorine-chlorine bond, and we have measured it to be 242 kilojoules per mole. Well, what does that mean? That means that I'm going to need to apply 242 kilojoules of energy to try to break this bond. So bond enthalpies are always going to be positive values. They're always going to be positive values because they're endothermic processes, meaning that we're going to have to absorb a specific amount of energy before we can break this bond. Okay? And you may be wondering, well, Mrs. Warren, do you have a typo here because it has a capital D right next to this? It's not a typo. Usually when we write something in terms of bond enthalpies, we designate that we're talking about bond enthalpy by writing a capital D in front of that bond. So if you see a capital D and then in parentheses that bond, that's just indicating that we have a bond enthalpy. So it's just an easy way for a chemist to know, oh, we're talking about bond enthalpies. Okay, so in this case, on our table, we, in terms of our calculated or our table with all of the bond enthalpies that we can find, they're average bond enthalpies, meaning that in this case we have methane. And if I wanted to think about breaking apart methane, I want to break all of the bonds in methane. Well, I have a carbon-hydrogen bond here, carbon-hydrogen bond here, one here, and one here. So I have 4 carbon-hydrogen bonds here, and all of them are the same. I mean, they're all equivalent. They're all carbon-hydrogen bonds. And to break apart all 4 of those bonds, I know that the bond enthalpy is going to be 1660 kilojoules. Now, that's for all 4 bonds. So then what would be for just one carbon-hydrogen bond? Well, I could do 1660 divided by 4, so that should give me 415 kilojoules. So we could find that average bond enthalpy for just one carbon-hydrogen bond if I know that all of these are equivalent, and then I know the total bond enthalpy for this was 1660, then that means one carbon-hydrogen bond would just be this divided by 4, so it gives me 415 kilojoules. But I may not always have methane. I may have something else that may be into play here, which I'm going to skip that last slide, guys, sorry, because I'm talking about these average bonds. So these are average bond enthalpies because I may find that it may be like 412 for a carbon-hydrogen bond, or maybe 417 kilojoules for a carbon-hydrogen bond before it breaks. So they're average because the CH bonds in methane, like maybe we just saw, are a little bit different than the CH bonds of maybe in something that's like chloroform, CHCl3. So because all of them are different because their interactions with the other molecules that they may be attached to is also going to be different. So on our average bond enthalpies on our table, we're going to see that these are just averages. They're just averages. So carbon-hydrogen bond, on this one, the average is 413. So I could use that value. You see here that we have a bunch of single bonds up here, but we could also talk about how much bond enthalpy, or we could say how much energy do we need to break a carbon double bond. Well, that's 614 kilojoules per mole. Well, what about a carbon-oxygen triple bond? That's 1,072 kilojoules per mole. So it should make sense, too, that the single bonds aren't going to be nearly as high in energy as what these multiple bonds are going to be. It's going to take a lot more energy to break apart a multiple bond, and that should make sense logically as well. I want to go back to that last slide, guys. Sorry about that. I just wanted to make sure we kept going with the average. So again, this is table 8.4 in your book. It's also found in your appendix. And these are just average bond enthalpies for different types of bonds. Again, they're positive because bond breaking is an endothermic process. So energy is always released when we're forming bonds, and we're always going to need to absorb energy when we are breaking bonds. So energy is always required to break bonds, which is why all of these have to be positive values. Okay, so we have found, like thinking back to chapter 5, there were several different ways we could find delta H. We had it where we could use that table with like the standard enthalpy of formations to find delta H. We could have found it by using Q equals MCAT when delta H is equal to Q. There's those different ways. We can also, though, use bond enthalpies to determine delta H, to determine that change in enthalpy. So, and we can compare bond enthalpies. We can do that by comparing bonds broken to the new bonds that are formed. So in other words, my delta H of reaction is equal to, the sigma just means sum. So the sum of the bond enthalpies of the bonds that are being broken, so what bonds am I breaking, and we're going to subtract that from the sum, sigma, again, just means sum, the sum of the bond enthalpies of the bonds that are formed. So I could find, again, that change in enthalpy, this delta H of reaction, by taking the sum of the bonds that are broken and subtracting it from the sum of the bonds that are being formed. So let's look at an example of this. Maybe, for example, we have methane, CH4, plus Cl2, one diatomic, my chlorine, and that's going to make chloroform, CH3Cl, plus hydrochloric acid, HCl. So in this problem, we have carbon-hydrogen bonds that are being broken, and then we have a chlorine-chlorine bond that's being broken here. I am forming a hydrogen-chlorine bond here. I'm also forming a carbon-hydrogen bond over here, and I'm also forming a carbon-chlorine bond. Now, it says here, in this example, one CH bond is broken. I started with CH4. On the product side, I have here CH3. So that means I broke one carbon-hydrogen bond. So that's where I'm getting this one carbon-hydrogen bond that's broken. And then I formed one Cl-Cl bond. I did that by breaking this apart. So that's where we're getting one Cl-Cl bond is broken. What we formed was a carbon-chlorine bond, because I'm going to have the 3 hydrogens around carbon, and then it has that extra place to take in one more, so it's going to take in chlorine. So we formed a carbon-chlorine bond, and then we also formed this HCl bond right here. So if we're thinking about, again, that last slide that says I could find the delta H, I could find that change in enthalpy by taking the sum of the bonds that are broken and subtracting it from the sum of the bonds that are formed. Well, I broke carbon-hydrogen and I broke the chlorine-chlorine. So remember that D just means that we're going to use those values, those bond enthalpy values. And then I'm subtracting it, like we said, from the bonds that are formed. So I formed a carbon-chlorine bond, and I formed a hydrogen-chlorine bond. So I looked up the values on that table, table 8.4, and carbon-hydrogen has an average bond enthalpy of 413, and then chlorine-chlorine has a bond average enthalpy of 242. So I'm going to add those two together because those are the ones that we had to break. And remember, to break a bond, it requires energy. So these are our positive values. Guys, the reason I'm subtracting them from the ones that are formed is because those are needing to release energy. So technically these two will be negative, and I'm taking that into account by subtracting them, okay? So a carbon-chlorine bond, if I look up that value, is 328 kilojoules. A hydrogen-chlorine bond enthalpy would be 431. I can just simplify my math. If I do so, we're going to get an overall enthalpy change to be a negative 104 kilojoules, okay? So what this means is that this reaction is exothermic because the bonds in the products are going to end up being stronger than the bonds that are in the reactants. Let me say that again. We know that since that delta H is negative, this is an exothermic reaction. So when we had, let's go back to that last slide, when we have CH4, when we have methane reacting with chlorine, forming chloroform and hydrochloric acid, the reaction is exothermic. So again, that just means that the bonds in the product are stronger than the bonds that are in the reactants. So when it's exothermic, the bonds in the products are stronger than the bonds that are in the reactants. And it will be vice versa if I were to have a positive delta H, talking about then an endothermic process. So make sure that we have that down. I'll say it one more time so you know it's important. This reaction is exothermic, and that shows us that the bonds in the products are stronger than the bonds that are in the reactants. Okay. So, last thing. Okay, we already talked about this too. We can also measure an average bond length for multiple bonds. And it says as the number of bonds between two atoms increases, we know that the bond length decreases. We already talked about that. Or we've already talked about that before. So I know that my single bond is going to have a much larger bond length than if this is a carbon-carbon single bond. If I look at my carbon-carbon triple bond, that bond length is much shorter. And let's think about that. They're sharing they're sharing more sets of electrons, meaning that that attraction between them is going to be much greater. So it should make sense that the bond length would decrease as the number of shared electron pairs increases. Okay, now there's a couple different problems for using table 8.4, and you're going to have to use that table. So you can't just have one of these problems and not use the bond enthalpy table. So this would be, if this were a test question, I would, or the AP test would give you the bond enthalpies that you need to figure this out. So I would like it if you would please try these two problems. I want you to calculate the delta H using those bond enthalpies. So do these two problems for me, and we're going to check them at the beginning of class on Monday. This brings us into chapter 9, which is about molecular geometry and bonding theories. The first half of this chapter should be review for us. The second half of this chapter is going to be brand spanking new, and it's going to be awesome. So let's go ahead and start into pretty much just the review part. In terms of molecular shape, we know that the molecular architecture, or molecular shape of a molecule is going to be defined by the angles and the distances between the nuclei and what it's between that central atom and then what it's bonded to. So two big things are defining the molecular structure. Two big things define molecular structure. They're defined by the angles, and they're defined by the distance between nuclei and component atoms. Molecular architecture, or molecular shape, is defined by angles and distances between the nuclei and the component forms, or the component atoms. So what are those two factors? Angles and distances. So angles, distances. Hopefully we will never forget that. So the shape of a molecule is going to play an important role in reactivity. Things react the way that they do because of their shape. So if we can note the number of bonding and non-bonding electron pairs, that's how we can determine shape. So it's not just super important for us to understand the shape, but it's really important to understand how the electron pairs, whether they're bonding or whether they're non-bonding, are acting, or how many of them that we have, because then that's going to predict the shape for us. So in this chapter so far right now, it's super imperative that we know electron domain geometry. How many electron pairs do I have? How many bonding pairs do I have? And then also the molecular geometry or molecular shape, because it's the electron domain geometry that will dictate what the molecular shape is. Okay, so what determines the shape of a molecule? Well, my goodness, we just said that. Simply put, electron pairs, whether they are bonding or non-bonding, are going to repel one another. That dictates the shape of a molecule. So because these electron pairs are repelling, it should make sense that electron pairs are going to be placed as far away from each other as possible, because we want to minimize the electron-electron repulsions. So when we have a linear molecule, it's because we have these electron pairs. I have two electron pairs here, and the best way to minimize that electron repulsion would be for them to be 180 degrees or have 180 degree separation. If we have something that's trigonal planar, I have electron pairs here, here, and here. So all of them are separated by 120 degrees. It's best for electron repulsion if they're separated that 120 degrees if this is trigonal planar. So the electron pairs dictate the shape of the molecule. I cannot say that enough, that it is so important that we know the electron domain geometry, because if we know that, we can easily figure out the molecular shape. So by assuming the electron pairs are placed as far as possible from each other, we can thus predict the shape of a molecule. We need to then refer to what these electron domains are. What does that mean? We have two types of electron domains. There's bonding and there's non-bonding. So in terms of bonding, non-bonding, bonding would then indicate that I'm seeing this bond, there's an actual link from the central atom to another atom. Non-bonding would be where I would just have them, if I'm thinking about just the central atom, it would be where it's not attached to another atom. So I have bonding here, I have a lone pair, a non-bonding pair that would be here. And if I'm thinking about double bonds or triple bonds, we're only counting them as one electron domain, because it's just that central atom that's bonded to just that one element, whether it be singly bonded, doubly bonded, triply bonded. We're only going to count a double or a triple bond as one electron domain. So if I wanted to count how many electron domains this particular molecule has, I know that there's 1, 2, 3 bonding domains, because I see that it's bonded to 3 different atoms here. And then I also have this one non-bonding domain. So this molecule has a total of 4 electron domains. We also think about the electron domains in terms of the central atom. So I'm only wanting to look at the central atom when I'm thinking about the geometry, because it's that central atom that then has everything else branching off of it. So that central atom is the electron domains that I need to focus on. Okay, so thinking about then the electron domain geometry, and also thinking about then what the molecular shape would be, we have come up with a theory that's called the valence shell electron pair repulsion theory, which we call VSEPR. VSEPR just means this is the best arrangement of a given number of electron domains, so forth that one that will the shape or the electron domains will minimize the repulsions among those electron pairs, or among those bonding electron domains with the non-bonding domains. So VSEPR, this VSEPR theory just means that we're trying to show shape by minimizing as best as we can electron-electron repulsions. It's the best arrangement based on the number of domains for minimizing repulsions among those electrons. So we have some different electron domain geometries. We have a linear electron domain geometry. So this is table 9.1 in your book. We have a linear electron domain geometry. That means that there are 2 electron domains. I have trigonal planar electron domain geometry. That means there's 3 electron domains. There's a tetrahedral electron domain geometry, tetra 4, so there's 4 electron domains. Trigonal bipyramidal is an overarching electron domain geometry. That means we have 5 electron domains. And octahedral means that we're going to have 6 electron domains. So we can also now think about molecular shapes in terms of these electron domain geometries. So we have these big overarching groups. There's linear, there's trigonal planar, there's tetrahedral, there's trigonal bipyramidal, and there's octahedral. Those are the big overarching groups for the electron domain geometries. You will need to know AB2 is associated with linear, AB3 is associated with trigonal planar, AB4 tetrahedral, AB5 trigonal bipyramidal, AB6 octahedral. So let's continue on with this and we'll see. Guys, there's subcategories too that are for each of these, which we're going to get into as well. If we want to determine the shape of any molecule, we want to have some steps for this. So if we need to determine the electron domain geometry or the shape, first thing we have to do is draw our fantastic Lewis structure. So let's say, for example, we want to do ammonia, NH3. If I draw the Lewis structure for that, I'm going to get my nitrogen as the central atom. Why? Because it would be that, because hydrogen can't be. So nitrogen would be my central atom. Hydrogen's coming across, or coming out from each of them. I know hydrogen is good and stable. I would have 2 more electrons that I need to fill. Those are going to be filled on the nitrogen. So I want to count, or if I draw my Lewis structure, I can determine the electron domain geometry. How many bonding electron domains do I have? I have 1, 2, 3. So I have 3 bonding domains. And then I also have this 1 lone pair. So that would be my 1 non-bonding domain. So in total, we have 4 electron domains here. So because we have 4 electron domains, this is technically going to put us in that tetrahedral electron domain geometry. But sometimes the electron domain geometry is not the shape of the molecule. So that's where we start to define something called the molecular geometry. The molecular geometry is defined by the positions of only the atoms in the molecules and not of the bonding pairs. So in this case, we drew our Lewis structure. We know that technically ammonia should be in that tetrahedral electron domain geometry, but now I need to think about its molecular shape, which is technically trigonal pyramidal. So you have a table 9.2 in your book, because how did I know that that was trigonal pyramidal? We are breaking down from the electron domain geometries what happens if we have 0 non-bonding and all bonding. What if we have 1 non-bonding and 2 bonding? So let's look, for example, in linear, the only case that we can ever have for linear is when there's 2 bonding domains, 0 non-bonding domains. It's always going to be linear. The trigonal planar electron domain geometry has 2 different categories, 2 different subcategories. I could have 3 bonding and 0 non-bonding, and if I do, it's just called trigonal planar. So that means I have 120 degrees of separation here between all of those atoms. I have another subcategory though. What if I had 2 bonding domains and 1 non-bonding domain? Well, we call that bent. This molecule then would have a molecular geometry that's bent. If we go to the next electron domain, tetrahedral. Tetrahedral, if it has all bonding domains, no non-bonding, it's just called tetrahedral. So if I see that I have all bonding and no non-bonding, then that just means it's going to be called the same as the electron domain geometry. Let's say in this case we have 3 bonding and 1 non-bonding. That name is going to be called trigonal pyramidal. So the example that we just did of ammonia falls under this category. We knew it had 4 electron domains, meaning that it fell under the tetrahedral electron domain geometry. So then I have to determine which molecular geometry would it have. Well, it has 3 bonding, it has 1 non-bonding, thus meaning it's trigonal pyramidal. If I go down here to the last subcategory then of this electron domain geometry, if I have 2 bonding, 2 non-bonding, also I'm going to get bent here as well. Still moving on, if we go to the 5 electron domain geometry, we have 4 different subcategories here, and you can go through those. Same thing for 6. If I look at 6, I have 3 subcategories here for 6. Do you need to know this table? Yes, you do. You will have to memorize this fantastic table. If you don't, there is no way you're going to be able to answer any of these questions on that AP Chemistry test in terms of molecular geometry. I will give you a quiz on Monday over molecular geometry and electron domains. So I am expecting that by Monday you will know these. So I would start focusing on this now. Super important. Okay, so in terms of our molecular geometries, so if we think about just removing one atom pretty much at a time, then we're going to see that there's a change in the molecular geometry. So if I'm in that tetrahedral group, if we have 4 electron domains, and this atom is now gone away, then I'm going to get trigonal pyramidal. And that's because I'm going to get this trigonal pyramidal because I'm just removing that, so I'm left with this shape here, and that non-bonding pair is just still right here. So I still have electrons that are here, it's just that they're not bonded. So I'm just taking away one atom at a time if I'm thinking about their molecular geometries, okay? So if, again, just tetrahedral, taking away this one atom leaves me with trigonal pyramidal. And it's not that I don't have anything here anymore, I just have that lone electron pair. And then here we're taking away another atom, so I have an electron pair here and an electron pair here. Okay, so this is just talking about pretty much what we just said. In the linear domain, there's only one molecular geometry, which is linear. Also, if there are only 2 atoms in the molecule will be linear no matter what the electron domain is. So if there's 2 atoms in a molecule, and that's it. Like let's say we had HCl, I have hydrochloric acid. It's linear because there's only 2 atoms there. There's only really one way that we can orient them, or only one way their shape can be, which is linear. Still, just continuing on saying what we just said, the trigonal planar, there are 2 molecular geometries with trigonal planar. There's the trigonal planar, or there's bent. So I took away one of those atoms, and instead we have an electron pair here. So this gives me a bent structure. So it's trigonal planar if they're all bonding. It's bent if one of them is a non-bonding pair. Okay, so this says, use the Vesper model to predict the molecular geometry of the following. So we have ozone, we have SnCl3 with a -1 charge, we have SeCl2, just neutral, and then we have CO3 2-, we have a carbonate ion. Guys, I'm going to start with this part in class. We'll do these together in class on Monday, so this is where we'll start off. But I do want you to make sure that you know your electron domain and molecular geometries. I will give you a quiz for sure on Monday over that. Make sure you also do that one slide with those homework problems. I'll check those at the beginning of class on Monday, and I hope you have a wonderful weekend. I will see you on Monday. Bye.